Okay, next point. Remember when we had that conversation about how microstates give us too much information? So I want you to think about a situation. I want you to think about how what was the word we used in order to say that there was too much information and we don't want to explain about the entire information. We called it distribution. So what is a statistical distribution? Imagine you have a piggy bank. That piggy bank has quarters, nickels, dimes, pennies. Imagining it? You break it. You want to buy I don't know, what do you want to buy?
A new piggy bank.
A new piggy bank? Okay, fine. You want to buy a new piggy bank. So you break it and you open it. And then you see lots and lots of coins fall out. Now, how do you keep track of those coins? You could either keep track of every single coin that you have, or you could be smart about it and make columns out of each kind, right? So the smart thing to do would be to do that. CI. So now, how does this help you? How many pennies do you have?
40.
So how many nickels do you have? How many dimes do you have?
At least 4.
Well, 4 dimes? I thought you had 10.
Yeah, at least 4.
At least 4. What about quarters? 5. Now, do you have to keep track of every single quarter in your case now? Do you have to keep track of every single penny that you have now? No. What you can do is you can simply say, oh, I have 40 cents here. I have $22 here. I have $1 here. And 5 quarters is what? 125? You have just made a statistical distribution. So instead of keeping track of every single penny, quarter, dime, coin in your collection, you can make distributions out of them. Does that make sense? Now, this becomes complicated when you are trying to think of quantum states, but this is fundamentally what the idea is. Get it? So what you're doing is you're taking like things and you're combining them together to form ensembles or distribution. Good? Okay, so now let's talk about this. So in statistical mechanics, distribution relates to the energies of individual particles in my system under consideration. So a distribution is the intermediate in detail between over elaborate detail of the microstate and the generality of macrostates. So in this case, in this coin example, what's the macrostate?
Statistical.
No, that's the distribution. So the macrostate is the entire piggy bank. Oh, macro, yeah. So microstate is each individual coin. But do you really have to keep track of every single coin? No, you just need to know how many dimes, how many pennies, how many this. And then what's the total amount? 1, 2, 3, 4. Wait, what's the total amount that he has? 1, 2, 3, 4. $4 and how many cents? 65 cents. That's your macrostate. Bobbleheads. Okay, very good. So now in my distribution, I have to define them for a distribution. We choose not to investigate which particles are in a particular state. Instead, we specify the total number of particles in the state itself, which leads me to two different things, two different definitions. So definition 1 and definition 2. Distribution in states. And distribution in levels. So what is a distribution in states? A set of numbers, N1, N2, N3, in particular states with particular energies. Where N1 has energy E1, N2 has energy E2, and so on. So generalizing it until Nj with energy Ej is called the distribution number. In general, that's the shorthand we use. Nj for the whole set. Are we good? Distribution in levels is a set of numbers N1, N2, N3, up till NJ, for which the typical number Ni is defined as the number of particles in level I with energy E, I, and degeneracy GI is the number of states belonging to that particular level. Shorthand for this case is Ni.